Hi, I'm Nico Micheletti, and I am sick at the time of recording, so please excuse my raspy voice. We are pumping more carbon dioxide in our atmosphere than ever before, and this is because we're using fossil fuels like coal and natural gas to sustain us. There are alternatives like wind energy or even solar energy, which is very popular on top of Montana State engineering buildings, or even geothermal energy, which is very popular near hot zones. But what about nuclear? Nuclear fission, the splitting of atoms. How does that work? What's the science behind it? Well, I'll talk about that today and more. Watch as this uranium molecule is hit with a neutron. You see how it splits? Well, it's forming two different atoms, but these two atoms don't make up the mass that was once the uranium molecule. So where did the mass go? Well, Einstein's theory of relativity says that mass and energy are the same thing. So when the molecule lost mass, it actually released a ton of energy. And there is a 5-second recap of what nuclear energy is, modern nuclear energy. But modern nuclear energy has a big problem. It's not that popular. And for good reason. According to the Pew Research Center, it's as popular as coal mining and fracking. And this is for valid reasons. Stuff like Chernobyl, where a meltdown in Russia killed 30, affected thousands, stay in people's minds, as well as Fukushima. And you also have to deal with the radioactive waste. It's not looking good for nuclear. Sometimes I wish we could just bring down the sun and use the sun's power. Wait, can you? I'm not talking about solar panels. No, I'm talking about the literal sun. The physical mechanism inside the sun, in the core of the sun, that gives us and sustains life on Earth as we know it. So let's take a closer look at the mechanism. So what we're going to see here are two hydrogen atoms combining into a helium, giving us tons and tons of energy. As discussed before, this is because of the theory of relativity. The two hydrogen weighs more than the one helium, so that loss of mass gives us a ton of energy. This is called nuclear fusion. Forget uranium, we don't need it. What we need is heavy hydrogen, which is found everywhere. It's in the oceans, it's in salt water. And carbon emissions? Forget about it. There are 0 carbon emissions. Also, you can't enrich the hydrogen and helium to give you nuclear weapons, which is a very big concern. Also, there's no chance of a runaway effect that happened in Chernobyl. If anything is off with the reaction, like in Chernobyl when there was, the reaction so-called quenches. It doesn't explode, it doesn't melt down, it's completely safe. Also, there's no radioactive waste. The only byproduct is helium, which is an inert gas. My class of 2020 through 2024, is probably asking, why aren't there any nuclear fusion reactors being built? Well, there is one, ITER, which is being built in southern France. It's a massive cooperation of multiple countries. And what you're looking at now is possibly the first ever nuclear fusion reactor. And again, you're probably asking, well, Nico, why only one? There are 3 of many requirements that must be met for a nuclear fusion reaction to occur: pressure, time, and heat. For pressure, I want you to kind of wave your arms around a little bit. Right now, you're probably experiencing 13 pounds per square inch where you're sitting. And for the core of the sun, where nuclear fusion occurs, we're going to need 3.1 trillion pounds per square inch. For time, well, stars take billions of years to form for the hydrogens to start colliding and breaking apart the magnetic barriers that separate them. For heat, well, ITER needs about 100 million degrees Fahrenheit. That's what they're aiming for their fusion reaction. So, yeah, these are the goals that ITER has to meet in their nuclear fusion reactor for us to be able to power the Earth with the power of the sun. Do we have enough time? Current science says no. We can't wait for them. Till then, we're going to have to stick with what we got, with alternative energy sources like wind, solar, hydro. If you're watching this, you're probably either in PSI 415 in 2021 with me, or a graduate of the MSU class of 2070. Now, I don't know much about you, class 2070, but I know you live near mountains, and I hope you still have access to one of my favorite beverage shops. You hopefully get to see my favorite animal, But we have a ton and ton of space here in Montana, and we utilize that space to make energy. And half of our energy is we sell it to the West Coast states. We're urbanizing and moving towards those states more than ever, so we're going to need to ramp up our energy sources in our rural states. Now, we've had legislation that's looked at nuclear energy, but we haven't really had action. What we see are polar bears swimming where they should be walking. We see hundreds of thousands of cars traveling the freeways, polluting our atmosphere with their old combustible engines. But what we have is you. You guys may not know this, class of 2070, but it was once a student who was walking down in front of Romney Hall that just wondered, how hot is it down there? Could we use that energy to power Romney Hall? And that's exactly what happened. All it takes is just one question. Sometimes the answer's right in front of you. Maybe you should ask, what's up there? What's going on up there that could help us to this day? Class of 2070, thank you for watching, and to my students, thank you for watching as well.